All right, guys, let's go through a quick recap of what we learned last week, guys. Basically, last week we talked about thermal capacity and also specific heat capacity, right? I told you guys that specific heat capacity is the one that is more commonly asked in your IGCSEs. Usually, you have to remember the formula that Q is equals to MC theta. Say it a few times in your head or voice it out verbally. Most likely, you'll be able to remember it. The only difference between thermal capacity and specific heat capacity is that it is missing the M component here, in the sense that the general formula is either going to be Q equals to MC theta for specific heat capacity, or it's going to be Q equals to thermal capacity multiplied by theta, which is for thermal capacity, guys. All right. Then after that, I also mentioned that different materials will definitely have different specific heat capacities here. Right. Obviously, the easier it is to heat up, the lower the specific capacity. That's why for things like metals, they are always relatively lower in terms of specific heat capacity, simply because it is much easier to heat them up comparatively to water, right? You remember last week I mentioned, like, if you boil water, you put that boiled water onto your table versus a heated metal spoon, the water will usually retain its heat more longer, simply because it has a relatively higher specific heat capacity, guys. Then after that, we did some questions here, and then I kind of rushed through this a little bit. Let me just go through this a little bit more detail, guys. Like I mentioned, energy can always be transferred from one form to the other. In this scenario here, we are basically transforming electrical energy into heat energy, right? And if you want to convert electrical energy into heat energy, first and foremost, you must remember the general formula, where power is equal to energy over time, right? Power is equals to energy over time. And I also mentioned that this energy could be any form of energy. It could be work done, it could be kinetic energy, it could be potential energy. In this specific scenario here, it is going to be heat energy, because we want electrical energy to heat energy, right? So from here, making the energy the subject, basically moving the T upwards, we're going to get power times time is equals to heat energy, right? And we understand that heat energy is going to be equals to MC theta. And thus, this gives rise to the new formula for converting electrical energy into heat energy, meaning to say, however much heat energy is supplied to a specific material, it depends on how much power we supply to the heater and how long of a time it takes for us to, how long are we supplying this power to that specific material, guys. Definitely, they will ask this in your IGCSEs, but of course, it is all back down to how you identify and extract the information, guys. Before we ended last week, I think I gave you guys some homework, right? I told you guys to do question 1 to 3, which I assume some of you guys did not do. How many of you guys did the homework, by the way, question 1 to 3? Can I have like a raise of hands on Zoom? How many of you guys did this, question 1 to 3? Very good. What do you mean so awkward to raise? Just click the button. I don't even need you to like physically raise your hand, right? But only one of you guys did it. The rest of you guys didn't do the homework at all. Bloody hell. You're supposed to do the homework, guys. Jewei, I assume you did it, right? Oh, Jesus Christ. Yeah, but anyways, we don't have enough time for this and today. Actually, maybe we do. Yeah, let's just go through this real quick. All right, if you look at this question here, first and foremost, obviously, you have to extract the information given from the question first, right? First question here says that the figure shows an electrical heater of power 400 watts. Obviously, I identify this as P first, right? Which is inserted into an insulated metal block. Given the mass of the block is 2.5 kg, this is obviously your mass, and its specific capacity is this amount. I'm going to make this as C. The first question they ask, what is the total heat energy supplied after 15 seconds, which obviously is your time, right? Looking at this information here, if they want me to find the heat energy only, right, and I'm given so much information, some students, they'll tell me that, oh, you're supposed to use the Q equals to MC theta formula. But if you were to use MC theta, you have the M, you have the C, but you do not have the change in temperature, meaning to say this formula is going to be invalid lah, right? So instead, what do I do? If I'm looking for heat energy could be part of the power equals to energy over time formula as well, right? So from here, I should identify that energy is supposed to be equals to power times time, which in this case here will be 400 multiplied by 15, which is supposed to give you 6,000 joules, guys. This is how you're supposed to attempt the question. While it is true that Q is equals to MC theta, given the scenario, if we do not have enough information, obviously we cannot just simply use the formulas, right? So be careful when you're substituting your formulas. All right. Then moving on to the second part, what is the increase in temperature, right? I'm looking for the temperature this time, given of the metal block after 15 seconds of the power supply, right? So right now, if I'm looking for increase in temperature, that is obviously going to be theta, right? And if it is going to be theta, it has to follow the Q equals to MC theta formula. From here, theta would have been equals to Q over MC. In this scenario here, since the previous question we calculated the energy supplied is 6,000 joules, right? Now, obviously, we're going to use the same thing also, 6,000 joules divided by my M, which was 2.5 kg, divided by my C, which was going to be 400. Press this into your calculator and you would most likely get some number. I don't know. 6,000 divided by 400. You'll get 6 degrees Celsius, guys. You're supposed to get 6 degrees Celsius. All right. Any questions with this part here? Anyone? But all of you guys didn't do the homework, right? So you wouldn't even know if there was a question because you wouldn't know what you don't know, right? Yeah. So anyways, for those who did not attempt this on your own, write down my answers, guys. If not, yeah, it's just GG. Okay, 6,000 joules and 6 degrees Celsius. I'll copy this down. Then moving on to the next part here. The mass of the cylinder is going to be 800 grams, which is obviously mass. I know for a fact that, guys, be very careful when you're doing the calculation. I've seen this 1,001 times, and it will definitely not be the last. A lot of you guys, because straight away you identify your information, you don't even look at the units, guys. You must look at the damn units because most of the time it is not going to be the right one, guys. Looking at this scenario here, 800 grams. Some of you guys may even use the calculation as 800, but I know for a fact that mass, the standard units for mass is supposed to be kg, guys. So essentially, it's going to be 0.8 kg here. I usually like to write it down before I even do the calculation. That way, you don't confuse yourself later on, right? So the heater delivers 500 watts, which is obviously the power, for 10 seconds, which is obviously the time. Find the specific capacity. You're looking for the specific capacity. So obviously the Q equals to MC theta formula must be used here, right? Of the aluminum, if it increased by 12 degrees Celsius, which is obviously your theta. From here, looking at the information, I have P, I have T, I have M, I have C, I have theta. It is none other than that formula, right? Power times time is equals to MC theta, right? From here, making C the subject, guys, C would have been power times time divided by M theta, right? In this scenario here, just substituting everything in 500 multiplied by 10 divide by 0.8 divide by a 12 here, right? Press everything into the calculator and you'll get somewhere around 520. You get 521. What's the units again, guys, for specific heat capacity? Jenlin, what's the units for specific capacity? Jenlin, are you there? Joules per kg degree Celsius, excellent. And we are, like I mentioned in the previous class, guys, you are not supposed to memorize the units, guys. Why? Because looking at the units itself, this is power times time, which is essentially energy in joules, right? This is in kg, and this is in degrees Celsius, right? So from here, I know for a fact that it's going to be joules per kg degree Celsius. Same thing for your Hooke's law as well. Most of the time, you guys don't remember the units of Hooke's law, right? Sorry, the spring constant, right, which is F equals to Kx here. If today you want to remember the units, you just write K equals to F over X, which is essentially newtons per meter, guys. That's why you get newtons per meter here for the units of the spring constant. Don't memorize it. Understand how you got there, guys. It is more important than everything else. All right. So final question. Given the mass of the metal is 0.5 kg, obviously this is the mass, and it has raised by 15 degrees Celsius. Obviously, this is going to be the theta. Find the total power. I'm looking for the power to the needed to be supplied to the heater for 15 seconds, given that the specific capacity is this. Yet again, looking at all the information I have extracted here, right? It's going to be M, there's going to be C, there's going to be theta, there's going to be power times time. So yet again, I'm going to go for the general formula, power times time equals to MC theta, all right? And from here, this time, instead of looking for C, it will be theta equals to power times time divided by MC. Yet again, substitute everything into your working, right? Then it's going to be like something like this. Mass, how much was the, oh shit, power was not 0.5. I'm looking for power. Oh God. Sorry, scratch everything I said. I keep thinking that we're looking for power, but we are supposed to look for, yeah, we are supposed to look for power. Oh, power is equals to MC theta divided by time. Right, yeah. So it's going to be 0.5 multiplied by 400 multiplied by 15 divided by a total time of 15 seconds. Cut. 0.5 times 400 is essentially 200 watts, guys. You're supposed to get 200 watts for question number 3 here. All right. Anyone's got a problem with these questions here? Anyone don't understand any specific thing that I've mentioned so far before we proceed on? I assume 100% absorption rate. All right, then let's move on to the next part here. For those who did not attempt it, make sure you at least copy down the answer, right? Because you will need to attempt it later on. Okay, the final thing that we're going to talk about today is basically latent heat of vaporization and latent heat of fusion. Now, in order to understand latent heat of vaporization and latent heat of fusion, let's imagine, guys, today, and again, it's story time. Let's imagine today I have a piece of ice here, right? Which is probably at negative 10 degrees Celsius. Ice, right? Ice could be anywhere from 0 degrees Celsius onwards, right? And in order for ice to change into water, obviously it has to melt. Water, let's imagine this is a puddle of water, can be anywhere from 0 degrees Celsius to 100 degrees Celsius. And in order for liquid to change into steam, obviously it has to go through boiling point, right? Steam could be anywhere from 100 degrees Celsius onwards, right? Now today, if we look at this thing here, let's imagine today, right? I have a temperature versus time graph. Today, I place this piece of ice inside a pot, right? I'm essentially supplying energy to the pot, to the ice, right? If I think about it, right, if I put this ice into the pot right now, what's going to happen is as the energy is constantly supplied to the ice, the temperature of the ice is supposed to consistently increase. And when the temperature consistently increases, by right, guys, the temperature time graph should look something like this, right? If let's say I have a temperature versus time graph of the piece of ice that is being supplied with energy or heat, right? By right, the temperature time graph should look something like this. But instead of having a straight line time graph, right, what essentially is really happening to the ice in terms of its temperature, it will go something like this. It will increase in temperature for sure, right? Then after that, it will flatline for a while. Then after that, it will increase in temperature again. Then after that, it will flatline for a while again. Then only it will increase the temperature again. I think you guys learned this in chemistry as well, guys. But first question here, can anyone tell me why does the temperature flatline at two specific points? What is going on there? Can anyone tell me what's going on or not during the horizontal flat lines? Or what's happening? what's happening here and here. Everyone of you guys take chemistry, right? Anyone here does not take chemistry? I think you guys learned this in the first chapter of chemistry, right? Oi, anyone can tell me what's happening or not? Melting and evaporating, very good. Okay, it is essentially going to, what's going to happen here is it is definitely going through melting and it is definitely going through evaporation. But why the energy that is supposed to increase the temperature at these specific points are when it is going through melting and evaporating, why does it not increase the temperature but instead goes flatline instead? What happens to the energy? So what's going on? Can anyone tell me what happened to the energy? Why it is flatlining here? To break the bonds. Excellent. Very good answer. It is essentially used to break the bonds. Guys, can you imagine this? At this specific scenario here, guys, at this specific time here, this is essentially the solid of the ice, right? Let me use a different color. This is essentially the solid of the ice, right? It starts off with negative 10 degrees Celsius. When it reaches the melting point, which is obviously 0 degrees Celsius, it starts flatlining. Why does it start flatlining? It's because all the energy that was supposed to increase the temperature of the ice right now is being used to break the bonds. And if you think about it, it kind of makes sense, right? Because solid particles, they look something like this, right? Solid, 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 solid here. When it changes state from solid into liquid, which is just the same thing, which is super disorganized, it is essentially because they break the forces of attraction, right? What happens is, right, instead of increasing the temperature here, guys, instead of increasing the temperature of the ice, the energy is actually being absorbed by the bonds to break them to change from one state to the other. It'll be the same when it goes from liquid into solid state, right? When it goes from liquid into solid state, yet again, it has to break the bonds, break, and eventually it will change into gas states here, right? So in your IGCSEs, they love to ask this question, you have to pay attention here. They'll ask you, what is happening on the horizontal flat lines? What happens to the energy? The answer is always a standard same answer. You're supposed to say that the energy that was used to increase the temperature of the ice cube is being absorbed by the bonds to change them from one state to the other. All right, I have the notes there. You don't have to write this down, guys. The notes will be somewhere down the line. Okay, so from here, essentially, if we focus on what's going on here, this first part here is going to be the solid state, right? Then this horizontal line is essentially the solid plus liquid state, right? Then after that, this is obviously going to be the liquid state. Once it fully melts out, it will convert fully into liquid state. Then after that, this horizontal line here, yet again, is going to be the liquid plus gas state. And finally, this here would have been the gas state here. It'll be the gas state here, right? And for those who do not know, guys, you know the Q equals to MC theta. Q equals to MC theta is the amount of energy supplied. The formula Q equals to MC theta. The condition is in order for energy to be supplied, the temperature should and must be changing, right? So Q equals to MC theta can only be used in these sections here. Q equals to MC theta can be used here. Q equals to MC theta can be used here, and Q equals to MC theta can be used here. Obviously, we cannot use Q equals to MC theta here because there is no energy change, right? There is essentially, no energy change, no temperature change, right? So instead of using the Q equals to MC theta, guys, when you are calculating the energy that is being absorbed by the bonds, this is when you calculate the latent heat of fusion and also the latent heat of vaporization, which in this case here will be either Q equals to MLF. Bear in mind, guys, LF is the same thing. It's just one thing, guys. It's like Q is one thing, M is one thing, and LF is one thing. Don't try to do your calculation later like, oh, you're trying to find F, then you're trying to find L. There's no such thing as L and F. It's just LF, one thing. Q equals to MLF is the latent heat of fusion, right? Fusion is essentially changing from solid into liquid or liquid into solid, whereas Q equals to MLV is the latent heat of vaporization. Guys, vaporization is either changing from liquid into gas or gas into liquid. And the word itself gives us the idea, right? It already has the word vaporization in it. Vaporization must be involving gas. So from here, you should remember fusion is solid to liquid. Vaporization has something to do with gas, right? So it must be something to do with gas. In this case here, it will be the liquid plus gas part. Okay. Yeah. Anyone's got any questions from this part here? Anyone confused or want me to repeat any specific thing that I've mentioned so far? So yeah, assuming everyone understands, right? Now, of course, last week we mentioned something about explaining specific capacity. How many of you guys can still remember how do we explain specific capacity? I'll give you a hint. It starts off with the formula. How do we explain specific capacity? Can anyone tell me how are we supposed to define specific heat capacity? It's quite important. It always comes out in IGCSEs, by the way. Anyone? Anyone can tell me how do you define the specific heat capacity of an object? Let me explain it again, since no one seems to be biting. Right. Usually in IGCSEs, they'll ask you this. So for those who still cannot remember, please pay attention. If they ever ask you to define specific capacity, Q is equals to MC theta, right? Defining specific capacity, first and foremost, you're supposed to make C the subject where Q is equals to M over theta. Once you have made it the subject, you can bullshit your way through a little bit, right? And then you'll still be able to get your marks, guys. Specific heat capacity is the amount of energy needed to change 1 kg of a substance by 1 degree Celsius, guys. You should be able to define it using the formula itself. I repeat again, specific heat capacity is the amount of energy needed to change 1 kg of a substance by 1 degree Celsius. Now, of course, on top of specific capacity, sometimes they will even ask you to define latent heat capacity as well, which is either latent heat of fusion or latent heat of evaporation. Now, today, if I ever want to explain latent heat of fusion or evaporation, right, first and foremost, yet again, same thing, Q equals to ML, right? Be it LF or LV, right? LF or LV doesn't matter, right? If they ask me to define latent heat of fusion or vaporization, yet again, I'm going to make it the subject L, F, or V is equals to Q over M, right? And looking at this, there's one more part to it. On top of just looking at the formula, there's one more part to it. Let me define it first, guys. Latent heat of fusion, let's say fusion, is the amount of energy needed to change 1 kg of a substance from solid to liquid without any change in temperature. This is the extra part in the latent heat of fusion, guys. If it is a latent heat of vaporization, if let's say it's latent heat of vaporization here, instead of solid to liquid, it will be liquid into gas. Same thing as well, no change in temperature. I repeat this again. For those who are asked to define specific latent heat, let's say they ask you to find the specific latent heat of fusion, right? You're going to say that specific latent heat of fusion is the amount of energy needed to change 1 kg of a solid into liquid without any change in temperature. If they ask you to define latent heat of vaporization, latent heat of vaporization is the amount of energy needed to change 1 kg of a liquid into gas without any change in temperature, guys. The keyword here is without any change in temperature. And if you do some questions in the past year paper later on, right, you'll always see that the word without any change in temperature actually carries marks, guys. So meaning to say it's actually a keyword, guys. Yeah, which makes sense also, right? Because if you look at the graph itself, latent heat of fusion is the amount of energy needed to change 1 kg of a substance from solid into liquid without any change in temperature, right? There's no change in temperature. Same thing for latent heat of vaporization as well, right? Latent heat of vaporization is the amount of energy needed to change 1 kg of a substance, 1 kg of a liquid into gas without any change in temperature, guys. Very important. You must be able to define it because it's quite a standard question with a damn standard answer, guys. It is essentially 3 marks. All right. Yeah. Anyone's got any questions from this part here? Mm-hmm. 100% absorption rate as well, just what I like. So yeah, if you look at these statements here, is essentially what I talked about in word format, right? The latent heat of fusion is the amount of energy needed to melt 1 kg of substance without any change in temperature. Latent heat of fusion, Q equals to MLF. You can draw an opposite graph as well, one that is going down like this, or one that is going up like this, which is the latent heat of vaporization, right? Latent heat of vaporization is the amount of energy needed to boil 1 kg of a substance without any change in temperature. Q equals to MLV. It will be the exact same graph, just in the opposite direction. Okay. Yeah. Can you guys copy this down real quick? I'll give you like probably 5 minutes to copy everything. Is it too small, by the way? Anyone can't see it? Anyone needs me to zoom in a little bit? Nah, this is the max back. Okay. Wait, 5 minutes, copy everything down into your notes. Then after that, we'll go on to the exercises. All right, be right back. Guys, copy down as quick as you can. And after that, we're going to go through some questions together. Okay, guys, everyone done copying? For those who are not done copying, sad. Let me just take a screenshot for those who are not done copying. All right, for those who are not done copying, let me know. Then I'll send a screenshot to you. But anyways, right, moving forward here, this is essentially just the word explanation of what we have been talking about so far, right? Just a different way of explaining it, guys. Looking here, fusion, during melting, the heat absorbed is used to overcome the bonds between the particles from solid to liquid. Vaporization will be the exact opposite, right? Not opposite, different states, right? During vaporization, the heat absorbed is used to overcome the bonds between the particles from liquid to gas. Always remember that vaporization is somewhat related to gas, right? So it's always going to be liquid to gas or gas into liquid. Whereas fusion will be the other one, right? If one is liquid and gas, the other one must be solid and liquid. It has to follow the solid, liquid, gas component all the time, right? So by definition, specific latent heat is defined as the amount of heat required or energy required to change the phase of 1 kg of a substance at a constant temperature, or in other words, no change in temperature, right? Anyway, you want to structure it, it's fine, but make sure you include the word that there is no change in temperature, guys. Very, very important. Okay, can you guys copy this down real quick? Then after that, let's go for some questions. One minute, guys, copying now. Okay, done. Then let's move on to the questions here. I think you should be able to do most of the questions here. Let me just show you how to do one of it, then you'll do the rest of it yourself. Let's go with this one here. Question number 2. Now, guys, pay attention. You're going to be required to do the rest of the 6 questions later on, guys. If you look at this question here, right, which is question number 2, right? First and foremost, yet again, it's most likely going to be a calculation question. This whole chapter is mostly calculation, guys, right? So look at the information here. The water of mass 0.5 kg, first and foremost, I identify that this is going to be mass. At 25 degrees Celsius, this is not change in temperature, guys. It is not change in temperature because it is just stating that it starts off at 25 degrees Celsius, right? So let's say this is temperature 1 here. It's put in the freezer compartment of a refrigerator. Obviously, the temperature is going to decrease, right? Calculate the amount of heat that must be removed to change the water completely into ice. Now, today, if I were to imagine the temperature versus time graph, let's draw a mini scale one. This thing here, this water starts off with 25 degrees Celsius, which is somewhere around here, right? Then after that, they say that it wants to completely turn into ice. In order for it to completely turn into ice, it is not here, guys. This here, this section here, guys, this section here is still going to be water, guys, because here is liquid, right? Here is liquid plus solid, and this part onwards is supposed to be solid, guys. Meaning to say, right, if I want to find the total amount of energy, I have to find this energy here, which is from the Q equals to MC theta, and I have to find this energy here to finally reach this point, because this is essentially where it turns into a solid, right? Completely into ice, which is equivalent to the Q equals to MLF here, guys. Meaning to say, in order for me to find out how much energy is needed to remove everything to change it from 25 degrees Celsius to completely ice, I have to find these two sections here, one section here and one more section here. From here, I know for a fact that it's supposed to be equals to Q equals to MC theta, which is this part here, plus Q equals to MLF, which is this part here. From here, once I have identified what I'm looking for, it's just a matter of substituting everything into the formula, right? Q equals to MC theta. If I look at the M, it will be 0.5. The C will be 4,200. The theta, in this case here, will be 25 degrees Celsius because it's ice, right? Ice is going to be -0. So it's not negative, sorry, so just 0 degrees Celsius. Plus with my MLF here, which is yet again still going to be 0.5, multiplied by my LF, which is 3.36 times 10 to the power of 5 here. Press this into the calculator, plus this into the calculator, you'll most likely end up with this number here. All right. Anyone unclear about this question here? This is essentially how you're supposed to find the total amount of energy. You have to take into consideration the liquid part, and you have to take into consideration the latent heat of fusion part, guys. All right. Anyone don't understand what I'm talking about? Anyone needs me to repeat this? 100% absorption rate as well. Copy this down. Do everything for the 6 questions. I'll give you guys roughly 15 minutes or less. 10 minutes, I think 10 minutes should be more than enough time to complete everything. Guys, do this for 10 minutes. Then after that, I'll assign you guys some homework before you end the day. Aha. 10 minutes, guys. Finish all the 6 questions right now. Okay, guys, are you guys done? Anyone stuck at any particular question that you cannot solve? Okay, if that's the case, right, can everyone check answers? We'll only be discussing the questions that you cannot do, guys. The first question should be 6.78 times 10 to the power of 6. The second one should be 1.01 times 10 to the power of 6. Always remember that you can only write it in 3 significant figures. And then the third one, which is actually the second question, which is the one I did, you're supposed to get 221,000, guys. Always remember your answer should be in 3 significant figures, regardless of whatever raw answer you found, right? And the third question here is supposed to be 8,090 joules. 8,090 joules, which is yet again correct to 3 significant figures. Oh, what's this? Okay, anyways. Oh, need help with question number 3? Oh, why? Which part were you lost? If I look at this question here, what do they want? Calculate the amount of heat required to change. Hey, wait a minute. This guy keeps calling me. Give me 1 minute, guys. 1 minute. Another donation question, another donation call. Anyways, yeah. Looking back into here, what do they want from you? Calculate the amount of heat required to change an ice cube of 0.08 kg and starting off with -7 degrees Celsius to steam that is 100 degrees Celsius. So if I were to draw the graph, it would be like something like this, right? It will be like starting from here, which is -7. So it'll be this part plus this part plus this part all the way until here, right? Where, oh, sorry, on top of this will be this part here, which is the steamer, right? This steam, this here will be completely steam already, right? Which is also at 100 degrees Celsius. So from here, first and foremost, I know that I need to find Q equals to MC theta for this part here, Q equals to MLF for this part here, Q equals to MC theta for this part here, and Q equals to MLV for this part here. Do you do this first? Do you do this calculation? Yeah. So Q equals to MC theta, it will be like 0.008 times with 4,200. You can actually straight away times with 107, because at the end of the day, these two will be the same thing. It's just like one that is times 100, one that is times 7, right? But it doesn't really matter. If you did both of it, it's still fine, right? Plus with your MLF, which is 0.008 multiplied by LF, which was 3.36 times 10 to the power 5, plus with your MLV, which is 0.008 multiplied by your 2.26 times 10 to the power of 5 here. Do you do this as a calculation? Most likely the only difference is instead of using 107, you did one which is 100 and another one which is 7. Right? -7, no. Hey, when you're doing the Q equals to MC theta, this is change in temperature. It doesn't matter if it's 0 to 7 or -7 into 0. The change in temperature is still going to be 7, right? There's no vector for change in temperature. You get what I mean? Yeah, most likely that's where you did wrong, right? Then if you did everything else, then most likely you'll get the correct answer. Yeah. Yeah. Okay. Go do your corrections later on. Okay. Then question number 4, check your answer, guys. It's supposed to be 0.025 kg. Right. Then question number 5 is somewhere around 4.3 kg. And question number 6 finally is 50,200 joules. 50,200 joules. Power what? Jen Lim, which question are you referring to? For the weight? Which one? Question 5 or 6? 0.25 kg of steel ball at 80 degrees Celsius is placed on a large block. Calculate the mass of the ice melted by the heat from the steel ball. Okay, question number 4 here is basically another thermal equilibrium scenario, right? Because it has a steel ball that is being placed onto this block of ice here. This steel ball starts off with 0.25 kg and it is at 80 degrees Celsius, right? Then you're looking for how much mass this thing melted, right? Given that the specific latent heat of fusion is going to be 3.36 times 10 to the power 5. From here, yet again, like the one we did last week, you're supposed to understand that the amount of energy lost by the ball is the amount of energy gained by the ice. From here, the only scenario is that the ball, assuming it loses all energy, which means to say it goes from 80 degrees to 0 degrees Celsius, it will be mc theta, right? However much this energy is lost from the ball will be supplied to the ice cube, right? Which is in this scenario here, MLF, right? So from here, just substitute everything in, you should be able to get the answer. You understand what I'm talking about? Yeah. And then most likely the second question, question number 5 here would be the same thing as well. Some ice cubes are put into hot water at 90 degrees Celsius until all the ice melts. If the mass of the hot water is 3.8 kg, what is the mass of ice needed to form water at 0 degrees Celsius? Yet again, thermal equilibrium law, right? The energy from the water is transferred to the ice, or the ice is transferred into the water, which yet again is going to be Q of the ice cube is equals to the Q of the hot water, right? In this case here, it will be MC theta is equals to MLF. Same thing also, we're looking for the M here, right? Which is MC theta divided by LF. Substitute everything in, most likely you'll get the answer. You understand what I'm talking about? Yeah. Then question number 6 should be quite a straightforward one. It's just multiply only. Make sure you change your units. 0.8, then you should be able to get the answer. All right, guys. Any other questions from this part here? Okay, if there's no questions, let me assign you guys with some homework, guys. Now you see all these questions at the bottom here. Yeah, this is going to be your homework. On top of that, I would highly recommend you guys start off with some Google Sheet questions. Let me send it to you guys right now. Do the Google Sheet question first, guys. It's always recommended that you do the ABC questions first. It's easier to understand that way. Then after that, you do the paper 4 questions, and you'll have some knowledge of what's going on. Okay, so 2 sets of homework, guys. Question 4, I got 2.5, not 0.2, 2.5. Are you substituting everything incorrectly or not? Okay, let me do this last question before you guys go. Q equals MC theta. The steel ball is going to be 0.25 multiplied by 420 multiplied by 80 degrees Celsius is equals to M 3.36 times 10 to the power 5, right? Wait, let me do the calculation. 0.25 times 420 times 80 divided by bracket 3.36 times 10 to the power 5. Did you bracket it, Natalie? Most likely you did not bracket it, right? You divide, then you times, right? Oh, yeah, but if you do the calculation properly, you should. Yes. Yeah, it's supposed to be 0.025. Okay. Yeah. All right, guys. 2 sets of homework, guys. We'll discuss. Please do the Google Sheet questions that's supposed to be helping you, right? Then after that, do everything from here as well. We'll discuss the answers next week, probably add on some more questions. Then after that, next week will be exercise week, guys. Once we're done with this, after next week, we'll move on to the final chapter of thermophysics. Then after that, it's going to be exam time again. And I can see how well everyone's doing. Okay. Yeah, guys, if you have no other questions, that will be it for today. I'll see you guys next week. For those who have any questions, you're welcome to stay back, guys. All right. Yeah, welcome. Bye-bye. Hi, Hannah. Do you have any questions you want to ask?